Now, you know what this training is not? Well, it's not a lot of things, but it is not a networking course. We will have one soon, pretty sure. But for now, we'll just have to look at how the network in itself, or more exactly how the way the network is designed, impacts our security. The network is the backbone for any data that we're supposed to move from point A to point B. So any attack and any defense measure is going to rely at some point on our network. So network architecture is definitely something that has a strong impact on security. And well, when we talk about networks, the first thing that comes into mind is going to be an example of a physical network. That is the actual network that we can see and touch. So that's a place where we find, switches, routers, maybe wireless access points, and don't forget about cabling as well. That's also part of the network. Now, why are these devices important? Because they are all actual points of entry inside of our networks. So an attacker that has physical access to your network can open a wide variety of attacks, or pretty much all of them, exploits, perform man-in-the-middle, denial of service, stealing data, corrupting data, pretty much anything. So before we even reach that point where we have to think about security policies and firewall rules and how to match traffic using IPS rules, the first thing that we have to take care of is actual physical security inside of our physical network. And we are going to talk about actual physical security controls here. Don't forget about these either in real life or on the exam. And those physical controls are nothing else than the ones that you would probably expect that you would use to protect anything in real life. Locks, doors, fences, guards, even lighting or dogs that can protect any kind of perimeter or any kind of area that is supposed to be out of reach for intruders. So don't just think that you have to rely on smart, technologically advanced firewall rules and digital security mechanisms to keep the bad guys out. Sometimes a simple door or a proper lock can also keep the bad guys outside of your data center. Okay, then perhaps you're not going to be using a guard dog to protect your switch. How would that look like? But it might be a useful addition to the night guards that patrol your data center premises, especially if nobody else should be around at night. And also don't just think about a data center. Don't forget about your employees and their workstations that become exposed during the night or during outside work hours. Those are still points of entry in your network, and those computers still hold confidential data. So these are the physical controls that you should have in place. Now, of course, don't forget about the logical controls as well. So that's where we actually talk about, mechanisms that make sure that you have proper authentication and network access, and all the points of entry in your network are digitally secured. This is where you'll find implementations under the name of network access control, for example, or network access protection, or protocols like 802.1x that ensure that only allowed devices or users can actually connect to your network. Now, of course, this assumes that the device or the user already has physical access to your network, and you're already at the stage where you have to decide whether to allow that access further or not. And then we have to focus on the virtual realm as well, because a lot of the infrastructure that we're using nowadays actually runs in a virtual environment, not necessarily inside of a cloud, but also in our own data center. Most data centers nowadays are virtualized, so pretty much any piece of software or operating system runs as a virtual machine or as a container. Now, apart from the introduction of the additional virtualization layer or the hypervisor, most of the virtual infrastructure, you might be surprised to figure out that it is not as different as you might expect from the physical or traditional way of running applications. We are going to be facing pretty much the same networking protocols. So you'll still find IPv4, IPv6 will still use ARP and DHCP to connect and communicate through a network. You'll still use layer 3 routes to navigate from one network to the next, and virtual switches. So most of the protocols that we're used to from the physical world are still going to be used in the virtual world as well. We're also going to find the same operating systems, because the virtualization actually enables us to run multiple operating systems on the same host, on the same machine. So we're still going to be running the same Windows system, the same Linux systems on different hardware, this time virtualized. From a networking and also security perspective, we're still going to be using similar devices. So we'll be using virtual switches and virtual routers, virtual firewalls, virtual traffic inspection devices, VPN endpoints. So pretty much anything that we are used to having physically in a data center is going to be found in a virtual version in a virtualized data center. But now it's not a physical firewall anymore, it's just a virtual machine with virtual network interfaces that most likely runs the exact same firewall operating system as your physical device from your data center, but this time runs it just like any other virtual machine right next to your applications. Now, the security story in the virtual environment isn't really that short, nor does it really have a happy ending, because going from physical to virtual, we are going to be facing a couple more security risks. Now, just to mention a couple of these, you have attacks that are generically called VM escape attacks. And the idea here is that separate operating systems running on the same host are supposed to be completely isolated from each other. They should not be able to even realize the fact that they're running in a virtualized environment, not to mention that they shouldn't be able to access each other's files and processes. A VM escape attack is a type of attack or vulnerability that targets a weakness in the implementation of the hypervisor. Now, the hypervisor is nothing else than a very simplified operating system. Its only purpose is to ensure isolation between the virtual machines and to ensure that those virtual machines have access to real physical resources on the host that they're running on. Now, this hypervisor, of course, is just a piece of software like any other. It might have some bugs, it might have some vulnerabilities, which, if successfully exploited, might allow a virtual machine to actually escape its confines and be able to access other virtual machines, their processes, maybe even whatever their virtual CPUs are executing, or even what files they're storing on the same host, which is dangerous from a number of perspectives. First of all, if you're running in your own data center, this opens you to the risk of having one application that gets compromised infect the rest of your infrastructure in your data center. So this can be a way for an attacker to pivot from one compromised machine to the rest of your infrastructure. Secondly, and a much powerful implication, is when you're running these machines inside of a cloud environment. Because inside of a cloud such as Microsoft or Amazon or Oracle or Google, most of the infrastructure is shared. That is, you are running a virtual machine on a very powerful server that also runs virtual machines for 10, 20, 50 other customers. Now, what would happen if such an attack would be possible and would allow just anybody to access any other customer's data running on the same cloud, on the same host? That would be very bad news for any cloud business in the world. So remember, VM escape attacks, at the moment, they are still considered a theoretical risk. There haven't been so many examples of VM escape attacks actually succeeding, but the risk is always out there. The risk of a zero-day attack that exploits a vulnerability that nobody else has realized has been there from the very beginning. A second consideration that you might want to take into account is the fact that virtual machines, just like physical servers, have to communicate with each other. So you might have two VMs that can talk to each other, but they're both running on the same host, the same physical server. Well, they will most likely be communicating over the internal switch, so the traffic is not going to physically leave that server. Now, what if you have a bigger data center or just more than one server, and you have virtual machines that need to communicate from one rack to another, from one server to another? Well, that traffic is most likely going to pass through the physical network, where you're going to find physical networking devices, where you will have the same risks that you're facing in a physical data center. So even if you are going towards a fully virtualized platform or environment, that virtualization is still going to run on physical hardware. So never forget this. If you value the traffic between your virtual machines, which is, by the way, is also called east-west traffic, then make sure that you secure that traffic whenever it leaves your physical servers, even if the other server, the destination virtual machine, is located just a few steps away. So be careful with security in general in the virtual environment. Not to mention that attacks are much less visible. inside of a virtual environment, because on some situations, attacks or exploits can happen within the same host. You're not even going to see that malicious traffic traveling over your physical network. Also, you might not be able to enforce the same security policies using the same devices that you had in your physical network. You might have to adapt to your new environment. Also, if you're misconfiguring security in a virtual environment, disasters can. So don't allow more virtual machines to communicate than strictly necessary, and even try to isolate different types of machines on different hosts, if possible. Another interesting topic here is SDN, that's software-defined networking. And this is an interesting one because I would have said maybe a couple of years ago that this is a new concept. It's not so new anymore. It has been widely developed and implemented worldwide. It hasn't exactly penetrated so much market just yet, so you're not going to see at every single step pure SDN networks implemented in companies. And the need for SDN was born starting from the original method of managing and using networking infrastructure. So up until just a few years ago, most of networking out there was just physical network devices. We had switches, we had routers, we had firewalls, and we had everything in one device. And by everything, I mean we had a management interface to administer that device. We had the decisions, the intelligence behind that device, the operating system that dictates how to manage traffic, how to filter traffic, how to route it on one interface or the next. And we also had the actual physical traffic forwarding built in the same box. So that's the way we've been doing things. That's the traditional switch or the router that you can buy even nowadays. Now, SDN tries to change this approach, and it actually tries not just to change it for the sake of changing something, but also because it's trying to solve some important management overhead issues and the risk of misconfigurations when network infrastructure, especially in large companies, becomes incredibly complex. And it also tries to address those issues in virtual environments where, creating a VM, a virtual switch, a virtual router doesn't cost you any money. You don't have to buy anything and install it in a rack. But that's also one of the reasons why a virtual infrastructure can quickly grow beyond your control, can get out of control. This is also called VM sprawl as an, let's say, more or less official term, simply because it doesn't cost you anything to spin up a new instance of a virtual machine. Everybody starts doing it, and people start forgetting about what those virtual machines should be doing. They start forgetting about what security policies they should be applied to those VMs, and so on. Now, a virtual machine is much easier to ignore than an actual big, heavy server that it's mounted in a rack, and its fans shout at you every single time you pass by it. So with so many physical networking devices and virtual networking devices as well, SDN attempts to abstract this network implementation, lets you focus on the big picture, while some intelligence inside that SDN implementation takes care of the nitty-gritty details of reconfiguring each network device whenever you want to make a change. So it moves the decision-making from the individual networking device, from that smart switch or that smart router that we said we used to have, to a centralized brain that is completely separate from the rest of the infrastructure, right? While the networking device is there to simply blindly accept and follow any commands that the brain tells it to do. It just implements them and makes sure that it moves the packets from interface A to interface B as fast as possible. So this SDN model is actually going to look something like this. So we're introducing something called the control plane, or also called the SDN controller sometimes. That's where the policy decisions are made. That's the brain that controls the entire software-defined network. Then we also have the data plane. That's going to be where the individual physical devices are located. That's going to be your actual physical router, your physical switch. They don't need any intelligence anymore. They simply have to listen to the control plane for any commands about routing traffic, applying security policies, inspecting traffic, reporting, and so on. They're just concerned with moving packets. That's it. And with third, we have the management plane. This is going to be the component that ensures that us as administrators can monitor and check the status of what's going on inside of our software-defined network. That's also going to be the interface that you use to input commands that get sent to the brain, to the control plane, and eventually to the data plane where the packets are actually going to be influenced by your configuration decisions. Now, we said that SDN tries to keep these ideas, these concepts completely separate, but it kind of looks more complicated, right? Now, it used to be so easy, have everything on one switch, just connect to that switch, create a policy, create an access list, and bam, you just influence the traffic flow, and that's it. What more do you need? Well, as we said, SDN tries to address some management issues, and also any kind of issues that occur in large-scale environments. So from a management perspective, think about the fact that you want to create a new VLAN on 100 switches. Now, this can be done in just a couple of clicks or just a couple of commands onto the management plane, which talks to the brain, the control plane, and makes sure that the proper instructions are generated for each of those 100 switches and they're all applied at the same time. So you have no typos, you have consistency, and you have a very consistent high-level overview of whatever is happening inside of your network. So no more human error. Consequently, if something bad happens inside of your network, you can either be instantly notified in your management interface, or you can even configure the brain, the control plane, to magically reconfigure the network around that failed segment or that failed device. Because again, the control plane has a high-level overview of everything that's happening in your network, which opens us to an additional benefit, which is automation or orchestration. Having all the intelligence, all the routing policies, the routing protocols, the security policies, anything that normally would be defined on a single device, having all this information in one centralized place allows us to reconfigure the network almost instantly. So whenever we need to make some changes, maybe temporarily reroute traffic or insert a new device in the network, a new virtual device that performs, I don't know, maybe IPS traffic inspection or any kind of additional virtual hardware, we can do this automatically. We can reconfigure the entire network in just a few commands. And we can also teach that centralized brain of the network to heal itself whenever it locates an issue within the network. Maybe route traffic around a failed endpoint, or maybe bring up a secondary firewall which is in standby in an active-passive high availability pair when the first one ceases to function or has a very high CPU usage. So we're not just moving the traditional intelligence from our networking devices onto this control brain, but we're actually bringing on top of it more control, more intelligence, more overview and automation on top of everything. And this is great news for admins. And by the way, everything that you're building in any cloud environment, be it Amazon, Google, Oracle, whatever it is, that's going to be software defined. And the networking that's running within that cloud environment, it doesn't matter if you're instantiating a Cisco Firepower next generation firewall or a Fortinet firewall or a Nexus switch. Any kind of device that you're creating inside of that cloud environment is going to be a virtual device, and the networking around it is going to be software-defined networking. How else would you think that you would be able to create an entire infrastructure in a cloud environment in just a few clicks? You simply cannot reconfigure hardware the way you reconfigure software. Now, from a security perspective, SDN can be extremely beneficial because it greatly reduces the risk of human error and also provides you with a better insight into any policies, any traffic flows that might be happening in your network in that control plane, right? That's very useful for security intelligence. But don't forget one thing. That brain, that centralized brain, is just another application that is running on your network and that is controlling your entire network. And that application can just as easily be compromised by an attacker. So win some, lose some, or better said, risk some. And just one mention here, with SDN, we said that we have this management application that communicates with the SDN control, that is the brain of the network. And this in turn is going to communicate with the actual physical devices that listen to commands coming from the SDN controller. Now, all this communication is usually done through APIs, application programming interfaces. And there are two keywords here that you should remember, at least for the exam, and that is the communication between the management application and the controller is traditionally called the northbound API, and between the controller and the actual physical devices, that's going to be called the southbound API. Now, another term that you will encounter very often, especially when you're interacting with public cloud providers, is the term of VPC, Virtual Private Cloud. Now, normally this is considered to be a kind of a network, a virtual network within that cloud environment, but in reality is more like a logical compartment of resources. It just happens that resources are very well compartmentalized by using separate networks. Especially because most of the infrastructure that we're creating, we're deploying in a cloud environment is somehow networking oriented. You're most likely not going to be creating many resources in a cloud environment that are not directly or indirectly connected to a network. Now, you are going to find these kind of cloud networks named in a number of ways depending on their vendors. So for example, Microsoft Azure here calls them virtual networks or VNets. On the other hand, AWS calls them VPCs, Virtual Private Clouds. You can see all the networking options in here. Oracle Cloud or OCI also calls them VCNs. That's Virtual Cloud Network. Again, networking configuration right here, but basically just used to separate or keep resources separate. And finally, Google Cloud Platform or Google Cloud mentions them as VPC networks. Now, inside of an actual VPC or virtual network, besides the actual virtual machines or entities that are running, are connected to it, you're going to find things that you might recognize from the physical world, such as subnets, route tables, gateways that connect you to the internet, DHCP options, public IP addresses. You can perform NAT for private servers, security, of course, using ACLs and firewall rules, DNS rules, VPN endpoints, and so on and so forth. So you're going to be focusing on a lot of the traditional networking knowledge and networking concepts that you've preferably remembered from the physical world. And speaking about VPNs, now that's another way to design your network. That's another component of a network design. You're probably nothing new here. I'm not telling you anything new. The concept of a VPN, it's widely spread. I'm sure everybody has used one at some point in life up until now. Basically, it's about a secure tunnel through a public infrastructure. So a way to remotely access some resources from a remote location and gain access to those resources just like you would normally have access if you were in the same network as your destination. So what do we use VPNs for? So first of all, for remote connectivity. If you want to access some private server from your company or from your home, you can create a VPN endpoint, connect to that VPN endpoint, and if everything is configured correctly, your computer is going to behave just as if it were locally connected to the same network as your remote resource. So that's remote connectivity. Now, secondly, we have security. Or most of the time we have security, and that is because if you think about a VPN, most people are going to think about the fact that the VPN is encrypted. But by its definition, a VPN doesn't assume any type of data encryption. A VPN is just like the name says, it's a virtual private network. So it basically takes care of just the isolation part of that networking access. And that's it. It doesn't say anything about security in there. And keep this in mind, especially for the exam as well, because CompTIA likes to catch you with these small caveats. So a VPN is by definition not necessarily secure. It can be, of course, and most VPNs out there are secured, but it's not part of its default nature. Now, of course, if we think of about a VPN as being an encrypted tunnel, a secure tunnel, that means we are protecting whatever data is being sent through that tunnel. But you have to still keep in mind the fact that opening yourself up to VPN connections from the outside is basically nothing else than increasing your attack surface. The VPN endpoint, if it has to be accessible from the internet, from any location out there, then it's also accessible for attackers out there too. So make sure that you properly authenticate users and devices when they attempt a VPN connection inside of your company. You can even go as far as implementing two-factor authentication or multi-factor authentication. Most VPN clients nowadays support this anyway, and you should be using this feature. Or you can go even further and implementing some clients that also perform some client posture checks before authentication. That is, the client also acts as a small security agent on the device that is trying to connect and scans that device before it attempts connection for, let's say, updates on the operating system, security patches, maybe performing even an antivirus or anti-malware scan on that host before allowing it to connect to the internal network. This is more of an enterprise level solution, but you will find this implemented in real life quite often. A very simple check you could be performing is the fact that the device owns a certificate signed by the certification authority of your company. So if it doesn't have that certificate and it's not recognized, then it's not a company device and you're not allowed to use that VPN connection. One final topic here on our discussion about network architecture is a recently introduced concept in cloud environments, and that is serverless architecture or function as a service. Now, if you look inside the AWS console, you can see here under the Lambda service that it says run code without thinking about servers. Now, how nice does this sound? Now, Lambda, it's actually a cloud computing service that is dedicated to running code, pure application code, or dedicated functions in an application without exposing any type of infrastructure. So there is some infrastructure in there. Of course, there are some computing entities, some virtual networks that run your code. You just don't see it. So this kind of requires a completely different approach, especially from a security standpoint. You have to treat this function as a service functionality like a black box. You don't know what's in there. You cannot secure the insides of that black box. So make sure that you can protect whatever is under your control. That is the inputs and the outputs that those functions accept and produce respectively. Now, if you want to play with this, give it a try with AWS Lambda. You can also access it in a free account. For Azure, you're going to find it under Azure Functions or Function Applications. And on Google Cloud, it's going to be called Cloud Functions under the Serverless Services category. Now, we could not possibly talk about network architecture without talking about network segmentation. What is network segmentation? Now, keeping things apart, right? That's what segmentation means. Why do we do this? Why do we want to segment a nicely working network? Why do we want to cut it in pieces? Well, any good networking admin would tell you that the first reason behind network segmentation is management and performance. In other words, having all your networking devices, all your hosts, all your servers into one huge network segment where everybody can talk to each other is going to create a very sluggish network, because all these hosts, all these servers can talk to each other, and all this entire environment here is sometimes called a broadcast domain. That's because any kind of broadcast communication, and we rely on broadcasts from the very first packet that we send between two hosts, from the very first ARP packet, address resolution protocol. We're going to rely on those broadcasts. Now, if you have hundreds or thousands of hosts in any single network segment here, the broadcast traffic is going to become huge, unmanageable, and your network is going to slow down. And not to mention the actual hosts themselves, because they're still going to be expending CPU cycles processing useless broadcast traffic. So from a management and performance perspective, we're going to try to separate this environment into more manageable, smaller networks, isolated networks. And there's also a security benefit. If one of these hosts, let's say this one here, gets compromised by an attacker, chances are it's going to be much more difficult for the malware or for the attacker to bypass this network edge and jump into a different network. It's most likely going to infect all the other hosts and the same network, and you'll be able to at least contain that attack to a single network segment. Okay, so how do we do this? Now, the most basic type of network segmentation is called air gapping. Now, air gapping is the simplest type of network segmentation because it doesn't involve the network at all. So with air gapping, you're basically isolating, completely disconnecting a host or a network segment from the rest of the network. So we're not talking about firewall policies here. We're not talking about traffic inspection policies that allow or deny your traffic. No, we're basically talking about unplugging the network cable. Wait, whose cable is this? And you might think that this is stupid, but it's also very secure. If you don't connect to any kind of network, there are no potential attackers or no potential exploits that you can fall victim to that come through a network. Now, as you can guess, this becomes really tough to manage, because if you don't have even management access in there, you're going to have to physically connect to that device or to that network in order to manage it, to perform some changes or to interact with it. So there are some alternative solutions that have been developed. For example, data diodes, which are physical devices that make sure that no kind of traffic is allowed to pass in one specific direction. That's because there are no internal circuits between those two ports. Some traffic might be allowed in the other direction, for example, to allow your isolated devices to perform updates and download some patches from the internet, but that's it. All the traffic is proxied and there is no physical connection between the input and output ports of a data diode. Where would you use this? As you can probably guess, you're thinking about, military solutions here, power plants, perhaps industrial solutions, any kind of network that relies on real-time operating systems that is supposed to have no outside interference, or any kind of system that wasn't designed or is not able to implement security. Thus, we try to isolate it from any potential danger. And another, let's say, a bit unexpected use of air gapping is for protecting certificate authority private keys. Now, as you probably know, in a PKI, in a public key infrastructure, we rely on a certification authority. That is just a server, right? That validates, that generates any other certificates that are generated by it. And those certificates are considered to be valid because they are signed with the private key of that certification authority. Just like a stamp or an identification card that is generated by your state authority. That's exactly the same trust that we have in those certification authority. Now, this means that the private key of that CA is something that must never be compromised. Otherwise, if the private key is compromised, all the certificates ever generated by that CA are going to be revoked, are going to be considered insecure. That's one of the situations where the private key can be stored on a separate machine, completely air-gapped, isolated from any other type of network, because we don't want to risk anybody reaching that machine, compromising it, and potentially compromising that private key as well. Then we have segmentation performed by networking devices, and we have segmentation at layer 2 performed by switches using VLANs, or segmentation at layer 3 performed by routers using separate routed interfaces or separate networks. Now again, this is not a networking training here, so I'm not going to dwell too much on this, but just to keep the story short, a VLAN, as the name says, a virtual LAN, is a logical construct inside of a switch that allows all the hosts within the same VLAN to talk to each other. Now, hosts in two different VLANs are not allowed by default to talk to each other because they're considered to be in separate networks. Now, two separate networks can be connected either by using a layer 3 switch, which has routing functionality, or an actual router. That's the purpose of the router, interconnecting different networks. Now, there's no point in separating two networks and then making them talk to each other back again, right? So the idea behind this type of network segmentation using VLANs or separate networks is that when we are actually routing from one network to the next, we also have the possibility of implementing some security policies. That is, actually specifying, I want this type of traffic to pass and I want this type of traffic to be denied. Which is basically somewhat similar to the behavior of a firewall. A firewall is nothing else than a router that connects different networks and can implement a bit more advanced security policies. We can look at the IP packets, we can look at the source and destination, we perhaps can look at layer 4 transport layer, we can look at TCP, UDP ports or ICMP code or whatnot. Or we can even, if we are using a so-called marketing name next generation firewall, we can also use at layer 7 or an application layer gateway. We can look at the layer 7, that's the application content within our networking traffic. So for example, we can have a simple network policy that says, I want to allow web traffic to this specific destination, that's going to be a layer 4 rule because it's going to be built based on the layer 3 destination and the layer 4 port number. Or we can have a smarter security rule that says I only want to allow Facebook traffic, but not Facebook chat or messenger chat. Right? That's going to be a layer 7 rule that requires you to have some sort of a firewall that is able to understand, look inside that traffic, that web traffic, because it all looks like web traffic, and figure out, well, this is a Facebook image, this is a Facebook post, this is Facebook chat, and I have to deny it. Then we have a specialized zone here called a DMZ. Now the DMZ, the demilitarized zone, is a network segment where you're supposed to place your publicly facing servers that belong to your local network. All right, so you have your local network and you have the internet. Of course, they are connected. And let's say you want to expose a website. You want to host your own company website. Now, one way of doing this is to just host that website within your local network and make sure that you allow traffic from the internet directly to that website host. Now, this is probably not going to be desirable because you will be allowing internet traffic and potentially malicious traffic to reach the internal network of your company. So a better decision for this would be to create an additional zone, which is going to be a completely separate networking segment from your local network, and that's going to be called a DMZ, a demilitarized zone. Now this DMZ here, of course, is also going to be accessible from the local network and from the internet, but most likely this junction here in the middle is going to happen inside of a dedicated box, which is most likely going to be a firewall. Now this dedicated firewall box here is going to have an interface that is pointing to the internet, another interface that is connected to your local network, and another interface that connects the DMZ. Now the purpose for keeping these interfaces separate is to actually be able to implement different security policies between all these three zones, the local network, the DMZ, and the internet. So for example, one type of security policy that you might encounter here would be allow all traffic from the internet to go to the DMZ, because that's where we host our public servers. All right. Now, on the other hand, of course, traffic coming from the internet and heading to our local network is going to be denied by default, because that's exactly what we don't want. We want to protect the local network from outside traffic. That's why we took the DMZ outside. So we're going to deny this. And of course, traffic from the local network heading to the DMZ is most likely not going to be allowed, because the DMZ is considered to be an insecure zone. It is exposed to the outside. It is the first one that is going to be compromised if an attack succeeds. So we're going to deny this kind of traffic here as well. Now, of course, if you're denying traffic from the local network to the DMZ, you're going to run into some management issues. So most likely there will be some type of traffic allowed here, management traffic going through a proxy, going through a jump box or a dedicated host solely for management purposes, because you will need at some point to, to configure the web servers, to update them, to update the content on your website and such. So you will have some limited access from the local network to the DMZ, but for no reason you shall allow your internal users to talk to the DMZ just like they would be in the same network. And well, speaking about things that run inside of a DMZ, we also have to introduce the concept of a jump box. Now, the jump box here is a dedicated machine. It can be physical, it can be virtual, that is created so that everyone is supposed to connect to it. Everyone has to go through it in order to access a different part of the network or some isolated network segment or some other resources, usually placed in the DMZ, as it needs to be accessible from the outside, or at least through a VPN. And you will find this design in a lot of companies where the VPN server, for example, is located somewhere within the DMZ zone simply because it needs to be accessible from the internet, right? From by outside users that need to connect to that VPN endpoint. And the host that is running this VPN endpoint is sometimes called a bastion host or a jump box. Now, well, the purpose of this jump box is to reduce the attack surface, while also, allowing some increased security authentication mechanisms, especially in the case of VPN servers, for example, so you can implement some better checks onto the clients that are trying to connect to your network. Now, the terms of bastion host and jump box are often used interchangeably, so they mean the same thing, and are frequently found in cloud environments where you have an entire infrastructure instantiated in some cloud provider, and you don't want to expose that entire infrastructure to the outside world, to the internet. So you just create a bastion host or a jump box like this, and everybody who wants to manage that infrastructure or connect to it has to connect to the jump box first, and then will jump from that box to the rest of the devices in your cloud environment. Okay, so that's it for today. I will try to keep these episodes as short as possible from now on, because 1 hour is a bit too long for anybody's attention span. So for the exam, make sure you remember that we talked about physical and virtual networks. We also talked about SDN. Make sure you're able to explain what's happening inside of an SDN and the basic components that make up an SDN. Then we talked about cloud networks, VPCs, VCNs and such, VPNs as well, virtual private networks. Make sure you don't confuse the acronyms here. And remember, we also talked about network segmentation, layer 2 segmentations using switches and VLANs, layer 3 segmentations using networks and routers, air-gapped networks, DMZs. Make sure we remember the purpose behind a DMZ, why we have it in there, especially from a security perspective, and the concept of a jump box or a bastion host. That's it for today. Thank you so much for watching. I hope you found this useful, informative and fun. Make sure you like and subscribe if you did, and see you next time when we will be talking about, what is this? Network traffic, packet and protocol analyzers, right? So we're still in the networking area next time as well. Thank you so much. See you next time.